If you've ever taken a computer science class, you've definitely met the linked list. It's always presented as this elegant, super flexible alternative to the kind of rigid array. But what if all that elegance comes at a steep, hidden price? A price we only really see when we leave the textbook behind and get into the real world of hardware and performance. That's what we're going to do today. Uncover the true cost of pointers.
I mean, this is the classic sales pitch, right? Arrays are clunky. You have to know their size ahead of time, and trying to stick an element in the middle is a total pain. Linked lists, they seem to solve all of that. You can grow them forever, and inserting or deleting a node is, at least in theory, a simple, quick operation. Sounds like the perfect data structure, doesn't it?
All right, so here's our game plan. We're going to start with that promise of flexibility. Then we'll dive right down to the metal to see what's really going on. We'll pit the theory against reality, figure out the right time to actually use these things, and even uncover some costs that go way beyond just speed. It all leads to one crucial insight: knowing exactly what you're paying for.
Okay, so let's give credit where it's due. The initial idea, the concept of these nodes connected by pointers, it's a really powerful abstraction. It lets us represent all sorts of sequences and relationships without being stuck inside one single block of memory. It is, for sure, an elegant solution to a very common problem.
And this, right here, is the heart of the matter. That flexibility, it isn't free. In computing, every single abstraction has some kind of cost. And the pointer, it's one of the most fundamental and maybe one of the most overlooked prices that we pay all the time. So to really get a handle on that price, we have to peel back the abstraction. We need to stop thinking about those neat little boxes and arrows you see on a whiteboard and start thinking about what's actually happening on the silicon, in the computer's memory. And listen to the language here. We're not talking about nodes and links anymore. We're talking about non-contiguous memory and explicit navigation costs. This means each node could be literally anywhere in your computer's RAM. So to get from one node to the next, the CPU has to go on this little scavenger hunt, following a memory address from one random location to another. That's the real cost of navigation. So what does that scavenger hunt actually look like? Well, for every single element you want to get to, it's a multi-step process. First, the CPU has to read the pointer's address from the node it's currently on. Then, it has to use that address to jump to a totally different, often far away spot in memory to find the next node. And you have to do this over and over and over again. This whole process, it's called pointer chasing. So why is all that jumping around such a disaster for performance? Well, it all comes down to this one critical idea: spatial locality. See, modern CPUs are ridiculously fast, but your main memory, well, by comparison, it's incredibly slow. To bridge that speed gap, CPUs use caches, these tiny, super fast pockets of memory. And they make a bet. They bet that if you ask for one piece of data, you're probably going to need the data right next to it very soon. So they just grab it ahead of time. And this is the core of the problem. Because the nodes in a linked list are scattered randomly all over memory, they completely shatter this assumption. When the CPU fetches one node, the next node isn't nearby, it's somewhere else entirely. The CPU's bet is wrong every single time. And all those powerful, clever caching mechanisms, they're basically useless. And that's the key takeaway. Following a pointer isn't some abstract, free operation. It often forces the CPU to just stop, to wait for data to be fetched from that slow main memory. We call this a cache miss. Think of it this way. Getting data from the cache is like grabbing a book off your desk. A cache miss is like having to stop everything you're doing, drive to the library downtown, and check the book out. It's a massive performance stall, and it's one of the biggest speed killers in computing. So this leads us to this really interesting clash, this collision between academic theory and what happens in the real world. In algorithms class, we all learned that a linked list insertion is O of 1, constant time, which sounds incredible. So why do they so often feel sluggish in a real application? Well, it's because big O notation completely ignores the physical reality of the hardware. It pretends every operation costs the same, but they absolutely do not. A cache miss, like we just saw, can be hundreds of times slower than an operation on data that's already in the CPU. Big O doesn't account for branch misprediction when the CPU guesses wrong about what your code will do next. Something pointer chasing makes much worse. Big O didn't see any of this, but your program, it definitely feels it. And this table just lays it all out, side by side. Look at the key differences here. Memory layout for an array is contiguous. It's all in a neat row. For a linked structure, it's fragmented. And that one difference directly impacts cache behavior. Excellent for the array, And just poor for the linked list. That one thing, how well the data structure gets along with the hardware's cache, is often why a simple array will just demolish a linked list in a real-world benchmark.
And that's the punchline, really. When you're working on systems where every bit of performance counts, those constant factors that Big O tells you to ignore, well, they're not just factors, they are the factor. The physical reality of your hardware completely dominates the theoretical elegance of your algorithm.
Okay, so after all that, you might be sitting there thinking, all right, so linked lists are just bad. But that's not it at all. They're not a bad tool. They are a specialized tool. The real key is knowing when the price they charge for all that flexibility is a price that's actually worth paying.
So, when does it make sense? You should probably reach for a linked structure when your program is just constantly inserting and deleting things from the middle of a list, when the size of your collection is just all over the place. And, really importantly, when you care about the order of the elements, but you almost never need to just jump to, say, element number 500. In those cases, the cost of chasing pointers might actually be less than the cost of constantly resizing an array. And we see these trade-offs made in the real world all the time. Adjacency lists for representing graphs are a classic example. The chains used in hash tables to handle collisions are another one, and things like compilers or even text editors often use really complex linked structures under the hood to manage code or text. In every one of these cases, the choice was intentional. The engineers knew the trade-off and decided, yep, the flexibility here is worth the performance cost.
But the cost of pointers isn't just about speed and cache misses. There's a whole other layer of engineering overhead that we also have to think about.
First off, memory overhead. Every single pointer takes up space. That's 8 bytes on a 64-bit system, and that really starts to add up. Then there's the cognitive load, right? It's just harder for our brains to reason about data that's scattered all over the place, which can make debugging an absolute nightmare. And finally, if you're in a language with manual memory management, pointers open up this whole world of nasty security bugs.
And this actually reveals this really powerful principle in software: simplicity, safety, and speed. They often go hand in hand. A simple contiguous block of memory, like an array, isn't just faster for the CPU. It's often easier to reason about, easier to debug, and a whole lot more secure.
Which brings us to our final and, honestly, the most important insight of this whole thing. We've gone from theory down to the hardware and back again. So what's the one big idea that you should walk away with?
This is it. This is the fundamental trade-off, boiled down to one sentence. When you choose to use a linked structure, you are making an explicit choice. You are buying yourself dynamic flexibility, and you are paying for it with spatial locality, which translates directly to cache performance.
And this elevates the whole lesson beyond just one data structure. This is a core principle of what it means to be a mature software engineer. Great design isn't about finding some mythical perfect solution that has no costs. It's about deeply understanding the costs of every decision you make, and then choosing to pay the right price for the problem you're actually trying to solve.
So, I'll leave you with this question to chew on. Pointers are just one example of a seemingly free abstraction that has a very real, hidden cost. So what other abstractions do you use every single day in your own work? And the real question is, do you actually know what you're truly paying for them?